Hi, this is the first video for the course Design of Mechanical Components, or if you wish, you can call the course Mechanical Design. Basically, in mechanical design, first of all, you need to design the mechanical components. So in this course, we will be introducing the important knowledge about design of mechanical components. And in the first step, we need to review mechanics of materials. The reason why we need to do that is because in the design of mechanical components, we usually need to worry about how much force is applied to a component and how strong the material is. So we need to understand the mechanics of the material and to figure out whether how much deformation will be caused by the applied force and whether the applied stress will be over its limit and causing some permanent damage, such as yielding or even failure, like breaking a material. So in this course, the fundamental starts with the mechanics of materials. Now, for every material, if you apply a force, it's generating some kind of pressure we call stress inside the material, and you need to first understand where are the direction of the force and also what kind of stress it's causing, and the orientation of those stresses will be very important. And if we observe a material in a different orientation, the values of those stresses will be different, because usually we specify the stresses based on how we observe the object, basically based on the coordinate. So suppose this is a small portion of the material of the component that you are analyzing, and you are observing this object on top of this coordinate. Then from here you can tell we specify specific symbols for the stresses applied on different planes and also different directions. If one day we change the orientation, like making an angular change of the coordinate, then we are basically observing this material in a different way. Then we still want to keep the habit of naming the stresses parallel to or perpendicular to our coordinate axes. Therefore, when you observe this whole thing in a different orientation, supposedly the values of those stresses should be different. And this is actually this practice of changing the coordinate and analyzing how the stresses are different in different orientation is actually a very important step in some future analysis. So let's focus on the names of the stresses for now. So we use sigma, and we have two indices, I and j in this case. So for the first index I, we specify the location of the stress. So for all the stresses on this plane, basically on the plane that is perpendicular to against the x-axis, we give we specify I as x, and the second index is representing the direction of the stress. So acting on top of this plane, the YZ plane, if there's a stress that is parallel to the x-axis, then we will specify the second index as x, like this one, which is acting on the direction that is parallel to y-axis. For this one, we will specify the second index as y. And similarly, we have sigma xz. And same concept applies to all the other stresses on different planes. So from here, we can already see we have 6 stresses that are applied on the surface and 3 normal to the planes. So we call those 3 are normal stresses, and the other one, the 6 ones that are applied on top of the planes, we call them shearing stress, because they are responsible for this kind of shearing motion. I'm sorry, I'm under some kind of dark light, so I hope you can see some hand motions I'm doing here. If not, you can watch some other videos that I made on YouTube as well. Okay, so in stress analysis, sometimes when we see so many sigma symbols, we would like to simplify them. So usually for sigma xx, yy, and zz, they would like to simplify them as just single x, sigma x, sigma y, and sigma z. So we everyone agree with this kind of notations, but if you are doing research in the future and you want to use certain kinds of symbols, make sure you define the symbols properly. Clarify what kind of notation that you're using. And for the shearing ones, instead of using sigma which could be confusing when we may have normal and shear stresses, so people tend to use tau. Just change sigma to tau. Okay, but there are some papers or textbooks they also use sigma. Okay, so in mechanical design, once we understand how much stress that is being applied on the material along on which position, along which direction, then we can try to figure out along that direction how strong the material is. So if I can represent the strength of the material in the same unit, then there could be a dimensionless ratio between the strength and the stress. So if I apply a stress that is having the same magnitude with your limit strength, then this ratio is 1. It's like if you apply a greater stress, you are off limit. So supposedly, based on this idea, your material may fail because it's over the limit. So if this is the case, you will have greater stress than your strength, so your N safety factor will be less than 1. If you have N equals to 1 exactly, that means you are designing just meet the limit of the material. You choose to design a geometry and picking up some kind of material with certain strength and apply certain force to generate stress, and the stress is matching how strong the material is. Then then this material, this part is under the situation of having n equals to 1. So is n equals to 1 good? Not really, actually, because if the force is a little bit stronger, then your material could be failing. Or if your material is not as strong as you expect, maybe the strength was just like averagely, if you have 10,000 pieces of same kind of metal, are you sure they all have the same strength? There could be uncertainty inside the material property or purity or so due to all kinds of reasons. You may expect some material to have some strength, but it actually is not as strong as you think. So with all those reasons, safety factor with n equals to 1 could be dangerous. So usually for mechanical design, we are looking for a design with safety factor greater than 1. So we have like a safe region for uncertainties that's everywhere inside the design, and those uncertainty won't kill you. Okay. Now, usually for mechanical design, we are dealing with elastic materials, which means when we look at the stress and strain diagram of the material, we are talking about the region, the linear region at the beginning. Like when the stress is not greater than the yielding strength, and the stress and the strain is having a linear relationship where the slope is your Young's modulus. Well, we're mainly focusing on the linear region. Why is that? Because let's say you are designing a motorcycle, and if you are designing in a nonlinear range, we know for metal, if a material is under a great amount of stress and it's already passing the yielding strength, it reaches a nonlinear region, and there's a great amount of deformation being generated, and it doesn't recover back to its original shape if you release the stress. So you are causing permanent damage. So let's say when you are riding a motorcycle and you carry a passenger behind you, and the weight of the passenger is applying external force to your motorcycle, and let's say you are designing you are using a really weak material, so the weight of the passenger is causing stress that is over the material's yielding strength. Then you are causing permanent damage, permanent deformation to the material. So once the passenger get off your motorcycle doesn't return back to its own shape. How would you like a design like that, right? So in the entire course, we are mainly focusing on design that is inside the linear region. That's actually good for us because the mathematics for linear elasticity is much easier than the nonlinear one. Okay, so in this slide, we are talking about applying force along a linear direction. So we are not talking about shearing force yet. Sigma is the stress, epsilon is the strain, capital E is Young's modulus, and we know due to this linear relationship, the stress is equals to E times your epsilon, and sigma YP, yielding point. YP stands for yielding point. Sigma YP represent the yield strength, and UT represent ultimate tensile. Over here, it's the ultimate tensile strength. It's like what's the extreme stress this material can hold. Okay, and usually sometimes in some kind of design, this value is also an important factor. So sigma UT is ultimate tensile strength. And over here, based on the definition of stress equals to force divided by the area, and strain equals to the deformation over its original length. And since they are having this linear relationship, we can put all these three together. We end up with this equation right here, and we can rearrange it. Then we can calculate how the deformation actually equals to PL over EA. P is the external force, E is the material property, L and A represent some key parameters about the geometry. So from here you can already tell deformation is very it's caused by three different things: what kind of material you are choosing, what kind of shape the geometry the object is, and how much force is applying. So if you can properly define those three based on simple calculation, you can estimate what's the deformation. Okay, so now what is causing normal stress? Bending is. And in mechanical system, we have this long geometries all the time, like a cylinder or a beam or a rod. So whatever that is long, it's very easy to cause bending stress inside this long geometry. So usually for stress analysis, the first problem that we solve is a bending problem. So let's get back to let's try to review what's gonna happen if we try to bend a long material like this. From here you can tell I'm already setting up a coordinate system x and y. So this is a 2D problem because everything is the same along the z direction. If you view from the right hand side, z is from left to right, and everything looks the same along z. So let's forget about z direction. Let's focus on the xy plane, and we are applying a pair of bending moment with the symbol of m at the left edge and also the right edge. The coupling, they are having the same magnitude and different direction. So the moment is balanced. But due to this pair of bending moment, the material inside this rectangle is under stress, and the top part, from here you can tell, if I make a cut at the middle and try to, if we have some kind of stress measure like a stress microscope, if we can visualize it, then if we cut them in half, we will see it. The top half of the material is under tension, pulling, and the second half is under compression due to the bending action apply onto the entire rectangle. But from here you can tell the top part of the rectangle will be lengthened if we bend it, and the bottom part will be shortened if we bend it. So if there's change of length, that means there's force, and if there's force, there's stress. So if the very top part is become longer and the very bottom part is becoming shorter, so there must be somewhere at the middle which does not have change of length, and we call this position as the neutral axis. Okay, and if we view this in a 3D view, the entire plane is neutral, so there's no deformation on the neutral plane or the neutral axis. Okay, so if there's no deformation on the neutral axis, that means there's no stress, no force, and that's why if you visualize at the middle, there's no force right here, and at the very top, it's having the largest tension force, and at the bottom, it's having the largest compression force. Okay, so if you try to visualize it in a 3D way, it's like this. Okay, And also, another thing I would like to remind you, when you check out the textbook, sometimes for a moment they would like to draw a double arrow right here to represent a moment. So just for you to know, this double arrow sign represent moment, okay, and it's following the right hand rule. Our thumb is pointing onto the this double arrow, and our four fingers represent the direction of the moment, if you forget about this. Okay, now the next thing we would like to do is to calculate the magnitude of this calculate how much stress we have everywhere along this cut or cross section area. So the way we do it is to use balance of moment. So if we make a cut, supposedly in statics we know for the entire original rectangle, we should follow, if this whole thing is our considered system, we should follow balance of moment. And even if we make a cut and we cut this whole thing into half, even for only the left part of this entire material, and if we treat this left part as our system, this half system still follows balance of moment, and this is how you can calculate stress everywhere. So in this half, and since we need to follow balance of moment, so the left hand side is making is basically a counterclockwise moment, and whatever on the right hand side, all those stresses is causing a clockwise moment, so they should balance with each other. So the only thing that we need to do right now is we need to write this balance equation, and on the left hand side of this equation we have this counterclockwise moment applied by us, and on the right hand side basically is how much stress that are generated at this edge of the material, and those will be responsible for the right hand side moment. So how do we have this right hand side equation? What we need to do is to use calculus. So here, that's considered a small portion of this area that is having a height of dy, and the position of this area is right at the height, right at the level of y, and we name this area as dA. Okay, so let's say at dA we have a stress of sigma, and by this figure, by our observation, we know it definitely is a function of y, because when y equals to 0, sigma is 0, and when y is c, the upper part, when y is at the upper part of this material, we should have the largest sigma. So at the middle, sigma basically is having a linear relationship with y based on this drawing. So this drawing is actually our assumption, because we assume supposedly the force is inside, it is linearly applied inside the material. So we assume sigma equals to ky. K is just some coefficient, and that we don't know what it is for now. Okay, so at this position we have stress of ky. If we do stress multiplying area, we will have force. So on this area, sigma y times dA, this is force. And what happens if we have force multiplying y. Y is the distance from the position to the rotational center. So that will be the moment that is caused by this force on top of the dA. So this is basically the moment that is caused due to the stress right here. Okay, so what we need to do next is to just sum up all the moment that is generated everywhere. So how do we sum up? We use integral. And we do integral from y equals to negative c up to y equals to c. So this is, I should write y equals to negative c to y equals to c. Okay, and since sigma y equals to ky, so we can reduce this equation into this. Now we have this ky squared dA over here. And since k is just a coefficient that doesn't change, so it could be moved out of the integral, and we can kind of take a look at what k is. And at the end, k equals to n over this huge integral. So what is this? We name this as I. What is I? I is the area moment of inertia. Okay, so if the geometry is having different kinds of cross-section area, I changes. Okay, because it's related to y. Y is the length along this direction, and also the area. So the width also will make your I change. Okay, so this is a review of a rectangle. You can Google area moment of inertia. You can see a long list, and this is just a part of one of the common shapes, the rectangle, and we are calculating I about the center of the geometry. Okay, and if we move the center, I changes. So this is important, and later on we will introduce a theory, parallel axis theorem, which tells you how to calculate I if the center is not, rotational center is not at the middle, not at the center of the geometry. Okay, so I will let you try this by yourself and to prove Ix and Iy. But what does Ix and Iy mean? Okay, so Ix means you are calculating I when there is some kind of rotation about the x-axis. Okay, x-axis. And Iy means the area moment of inertia when you are calculating some kind of rotation about the y-axis. But in our case right here, we know the axis about the from left to right is actually z, so that's why over here we use z right here. But this is a general figure that was captured from Wikipedia. So the x and y right here, sorry, the xy right here is different from what the coordinate system that we're using right here. Okay, so please don't be confused. Okay, so if this is y, if this is I, then we can put k equals to sigma over y, right? So we can end up with this equation, because sigma over y and y move back to the right hand side. Then we know sigma equals to my over I, and let's pay attention to this. Y is a function. Sigma is a function of y. So by changing y, by changing the position you want to observe, you can calculate sigma. You can know how much stress is being applied everywhere along the cross section. And how do you calculate it? It could be calculated by how much moment that you are applying on the left hand side, and also what's the position you are at, what position you are observing, y right here, and also I is a geometrical parameter. So it really depends on what kind of geometry you're having. Okay, so if you have a different shape, I changes. Okay, if you have or same material, different orientation, I changes. Okay, so now we understand stress depends on how much force or moment you apply, where you are observing, and also what kind of geometry you are studying. Okay, I'm sorry, there's a construction outside. It could be loud. Okay, now let's talk about shearing. So what's causing shearing onto like long geometry? Twisting. Twisting will be generating shearing stress. So in this case, we are showing a rectangular geometry because the analysis is going to be the same everywhere in every. It basically is axisymmetric. Okay, so we can consider the equations will be simpler if we study this in a cylindrical way. Okay, so similarly, we are applying the very similar equations right here, but completely different low conditions, and this time we are applying torque. There's a torque rotating about the right hand clockwise, and another torque another torque on the other end, but this is counterclockwise. Okay, and these two are causing twisting of the cylinder. Okay, and if you draw a dashed line from here, due to this twisting, this dashed line could be being twisted up to here. So there is a generation of angular difference due to the twist. Okay, so this is how much you like. What's the angle of your deformation? So we call this gamma. Gamma is basically the shear strain. Gamma is your shear strain, and the stress that is being generated on each on the cross section, the shearing stress, basically is tau, and we are focusing on small deformation, and the material is still within linear elasticity. So the shearing stress and the shear strain is having linear relationship, and the coefficient right here is your shear modulus G. Okay. Now, next, right here is something about geometry. How we get this, it can be observed from the figure of right hand side here. So if we take a look at this arc, okay, take a look at this arc. The length of the arc equals to the radius times the angle, so r theta. And also, if we take a look at this, like a triangle, but it's not triangle, it's like a curved triangle. Since in linear elasticity, this deformation actually is very small. You don't quite see it. So this drawing is exaggerating. So when the deformation is so small, this is very similar to a rectangle, or very similar to a portion of like a pizza pie. Okay, so this arc, the length of the arc is very close to this radius times angle here. So L gamma is also equals to the arc length right here. That's why these two can be the same. So if we are having this equality, we must understand it's based on the assumption of linear elasticity, which means the deformation is small. If we are dealing with soft materials and usually we generate large deformation, then definitely this equation is not valid. And also the stress strain material, the relationship won't be linear. So this whole thing needs to be corrected, needs to be upgraded to a nonlinear analysis. But not in this course. We are dealing with metal, and usually the deformation is small. Okay, if we put these two equations together, we end up with theta equals to L gamma over R. Okay, and also we can this came from the second equation right here, and if we put the first equation in, we know theta equals to L tau over R and G. So let's have a brief observation of this. So theta represents how much angle you have for this twisting. It's like telling you what's the angular deformation of your twist caused by the torque. And over here, we realize the theta is related to some geometrical parameters, L and R. L is the length of the cylinder, R is the radius. And tau, how much stress that is being generated, and also G, material property, the shear modulus. Okay, but we cannot get the last equation yet because we need to do calculus on the left hand side. So let's get back to the analysis on the left hand side, and then we can understand why we could have the last equation on over here. So on the left hand side, when we try to understand how much stress that we are generating due to the torque, it's based on the same trick from the linear problem, but here we are trying to balance the torsional moment. So due to this, so this is like if we make a cut, similarly, if we make a cut, and on one end we have so actually we are showing the front half of the cut. So one part of the material is under the external torque, turning counterclockwise, and at the cross section we will have some shearing stress, and that is responsible for clockwise moment. So the torque and the clockwise moment generated due to the shearing stress will balance. So the way we balance is to formulate this equation. On the left hand side, this is the counterclockwise moment torque. On the right hand side, this is basically all the clockwise torque that is applied inside the force. So how do we get that? We still assume this shearing stress is linearly related to the radius, the position. So at the middle, also this is a neutral axis. No stress, no force, no stress, no deformation, no angular change. So there's nothing changes at the center. But as we observe outward, and as the we are reaching at the position of radius of r, if we observe a very small area with the thickness of dr, and this is like a ring, and how much force, how much stress are there? We say there's stress of tau right there, and from here, because of that linear relationship, we're sure tau is a function of r, and we assume it equals to kr. What is k? Just a coefficient to represent its linear relationship. So there's tau r right here. Now so tau r is applied around this entire ring, everywhere on top of this dA area. So if we have the stress multiplying our area ends up with force. So basically, if we do that, this is the force applied against the dA and toward the tangent direction, tangent direction everywhere. Okay, this is the shearing force. And if we have that tangent force multiplying the radius, then this is this is basically moment over here or only. So if we can do an integral from radius equals to 0 to radius equals to r, actually at the end we could have a total sum of the right hand side as clockwise moment that is due to the shearing stress inside the material. So that's how we end up with this. And then we know tau equals to kr. We can put kr back to here. So we end up with kr squared inside the integral. K is not related to a, so it's a constant. It could be taken out of the integral. That's why we end up with an equation like this. K equals to your torque over this integral, and this integral is called the polar area moment of inertia. It's J. And what is J? J is actually here this is Ix, or sometimes people call Ixx. This is Iy. So J is Iz. The moment of inertia, area moment of inertia about the z-axis, and sometimes people just call it J. Okay, and J equals to Ix plus Iy. You can Google it or check your textbook. Now we understand the tau, the shearing stress everywhere inside the material, can be calculated like this. It's linearly related to R, linear proportional to R, and so how you calculate it is based on how much torque you have times what's your position. If it's located at R equals to 0, there's no stress. If it's at the maximum, it's at the capital R, the maximum, it will be having maximum stress. And down here we have J. J is a geometrical parameter. Okay, with this we can put it back to the equation on the right hand side. Now we end up with this. So how much deformation that you can generate could depends on how much torque you have, what's the material property you use, and also some geometrical parameters. Okay, you can kind of compare this with the linear equation right here. Okay, actually we could put this back to here as well, but I didn't do that. It's okay. So anyway, please review the slides and then try to compare. So sometimes that helps in your memory. Okay, now let's put those equations together and see what we have. In most of the time, we are analyzing a shaft, basically a cylinder. So what will happen if we are analyzing a shaft? What's the bending stress and the twisting stress? Okay, so based on what we had earlier, sigma equals to mr over I, tau equals to tr over j. R basically is half of the diameter. I could be calculated if you check the area moment of inertia of a circle. Basically I equals to pi over 4 times radius to the power of 4th, and R basically is d over 2. So at the end we have 32m over pi d cube. Okay, this is a very important equation and you will be using it for many times in this course. Please try to memorize it. And tau equals to tr over j, r equals to the diameter over 2, and j basically is half. not half, sorry, double of Ix, because J equals to Ix plus Iy, and Ix and Iy are the same because this is a axisymmetric material, so these two are the same. That's why J is doubled of Ix. So over here, this is pi over 2, not pi over 4. And due to since we have this, at the end we have 16t over pi d cube. Also very important equation because we will use it later on. Okay, now area moment of inertia of a shaft, I think I will keep it here. This is just a proof of how to calculate this. I keep it here for you to practice on your own. I think it's a good practice and get back to a lot of memory of calculus. Why don't you try it? Okay, I will leave it here. You try it and try to prove Ix and Iz. Okay, now yeah, I did comparisons. Okay, I'm not going to repeat those, but good comparisons. They all have very similar mathematical format, but different meanings, different directions, different types of force and stress. But the format of the equation looks pretty similar. Okay, now let's take a look at a problem inside a shaft. So right now this shaft is under a pair of torque and a pair of bending moment. Then we would like to analyze somewhere at the surface of the cylinder. So let's take a look at the top, like at the very top tip of this cylinder, highlighted by the drawing. And we are visualizing from top to bottom. Our eyeballs are at the top. We are visualizing from top to down. So if we do that, our right hand side would be x-axis, and our at the bottom, toward bottom, is our z. Okay, so due to the bending moment, if we observe this material right here, it's under tension. So there's left and right normal stress pointing out. Okay, and due to the torque twisting in this way, so on the right hand side of this material, there are like force pulling downward, causing a shearing force. So that's why there is a shearing stress right here. Okay, and on the left it's shearing up. And we know these kinds of forces are coupled. So if we are generating clockwise moment due to these two pair of shearing stresses, then we must have opposite directional moments in some other places. Then at top plane and the bottom plane, it's actually on the top is shearing left, on the bottom is shearing right. So these two are having the same magnitude but different direction. It's doing a counterclockwise generating counterclockwise moment, so they will balance. These two will balance with these two. So all four shearing stresses are having the same magnitude. So how large are they? The normal, based on our calculation earlier, this is the normal stress would be 32m over pi d cube. And what would be the shearing stress right here? It's gonna be 16t over pi d cube. Okay. Similarly, we're analyzing this position, and since this position is located at the neutral plane of your bending, it's gonna be a neutral plane based on your bending condition. So there's no tensional stress on the left and right. only shearing. Shearing is everywhere. Okay, so this material is under this low condition. So I wish you could understand what's happening, and in the future we may be analyzing the stress conditions everywhere. So you need to make sure you are able to draw this 2D diagram. And what are those? They are called plane stress problems, because there's no stress about the third axis. From here you can see there's stress on the first plane and the second plane, but there's no stress about the third plane. Due to the low condition we have, there's no force about the third direction. And similarly, there's no force about the third direction. Okay, so those are called the plane stress problems. Okay, that's the end of this video. I wish you understand everything of this video, and if you can watch this video repeatedly. And if you have issues with my English, I do have Chinese version, the videos in Chinese version, so maybe you can watch them both to understand more. Okay, thank you, and I will see you next time in the next